Hello everyone. In this video, we are going to talk about B1, that is thermal energy transfer, and this will be a two-part video. In the first part, we will talk about some basics of temperature, heat, thermal energy, and how do we transfer that heat to change the temperature or change the state of a system. And in the second part, we'll talk about methods of heat transfer like conduction, convection, radiation. Okay. So in the first part, the temperature is measured as average kinetic energy. Okay, temperature, it is very simple thing to understand. Like individual particles have different kinds of energies, and when we average it out, that average energy, kinetic energy, is related to the temperature. The relationship can be directly given by this equation, that is average kinetic energy is equal to 3 by 2 kBT, where kB is a Boltzmann constant, and this is given in data booklet. Its value is 1.38 into 10 raised to minus 23. Okay, this temperature always has to be in Kelvin. Okay, and we can relate this average kinetic energy with average speed. So considering V as an average speed and M as the mass of a single molecule, so this is very much important. It is not a mass of an entire gas, so it is the mass of a single molecule. You can take mass or a molar mass as well, it works. But important thing is this relationship, the average kinetic energy is half mv square is equal to 3 by 2 kBt, leads us to a relationship that can help us find average speed of a particle. Okay, there has been questions in past where they can ask what is the graphical relationship between v and t. So since v is directly proportional to root of t, you will see a graph with a decreasing gradient. Similarly, they can ask relationship with average speed and the mass of a molecule. Then you can see there is an inverse relationship. So you will see a decreasing graph. What is internal energy? So since temperature is related to average kinetic energy, we want to define a internal energy of a gas or particle, or let's say a system of a particles. Now it can be solid, liquid, or gas, it doesn't matter. But internal energy is something that exists for all the materials. Now internal energy is different from mechanical energy. Means, for example, if I have a ball, okay, a rubber ball, and if I throw that ball to a certain height, then what is changing for that ball is the physical kinetic energy and the gravitational potential energy. Now these energies are mechanical energy. But if that ball falls on a ground and let's say it deforms, that force will exert some kind of a force on the internal particles or internal structure of the rubber itself. And what will happen? There will be some kind of internal energy that is going to change. The ball might heat up because those particles are squeezed to a certain length. So that kind of a change where the particles are affected, that constitutes the object, that energy is the internal energy. Okay, so internal energy is something that is what we constitute of individual particle, and then physically that object moving to somewhere to a certain position or a certain speed is mechanical energy. Okay, so internal energy is defined as sum of total kinetic energy of the particle due to the random motion. Okay, it can be motion, it can be vibrational motion also, that is in solid. And we have to take in consideration the potential energy and total potential energy combined of all the particles due to their intermolecular forces. So the intermolecular bonds basically encourage that potential energy. Okay, so in solids the bonds are such that the particles vibrate like a spring. So that is the potential energy stored in the bonds. Okay, and as the bonds changes, as the bonds break, we can see that there is changes in potential energy as well. Okay, the internal energy as usual is measured in joules. Then we will like to define heat as well. So heat is the amount of thermal energy transferred from a region of high temperature to the region of low temperature. So how much heat is transferred is simple, like we call it as heat. It is given as Q and measured in joules. Now, whenever we give heat to a certain material, there are few possibilities that can happen. The one of the most obvious possibility is that if I heat a material, its temperature is going to increase. Correct? So that is one of the possibility. But what is the other possibility? The other possibility is that whenever I give a heat to a certain material, it will change its state. Like for example, if I give a heat to a ice, it will melt. So changes in state is also possible. Okay. So we will try to calculate now mathematically how much heat is required to change state or change the temperature of the material. Okay. So if we supply heat that leads to change in temperature, we can calculate the change amount of heat required to change the temperature by this formula. Q is equal to mc delta T, where Q is the heat supplied, m is the mass of the substance, and how much it depends on how much mass you are providing, how much mass uh, is there present, then the specific heat of the material. So it is very much important the specific heat capacity of the material to be known, so that in order we can calculate how much heat is provided. The specific heat capacity is unique for every material in a particular state. Like for example, a water will have a different specific heat capacity, and the state of water, like let's say ice, the ice has also a specific heat capacity that is different from specific heat capacity of water. So every state for every material, the specific heat capacity is different. Okay. And the last parameter is the change in temperature, how much temperature we like to change. So we can define specific heat capacity as heat required per unit mass to increase the temperature by 1 Kelvin or 1 degree Celsius. Now, one thing that I would like to make a note that the change in temperature, okay, whether it is in degree Celsius or whether it is calculated in Kelvin, it doesn't make any difference because we are talking about differences in temperature. Okay, usually whenever there is a single temperature, not a temperature difference quantity, I will still recommend this to be taken in kelvins. Okay, but when we are taking temperature differences, then it's fine to work with degree Celsius as well. There is no problem in that. Whenever we are taking change in temperature, always I will like to refer as a higher temperature minus the lower temperature. Okay, so that will always make sure you are using correct sign convention. Okay. uh, Most of the students also have questions like, if I have like ice going from -5 to -0 degrees Celsius, so in that case I will take my delta T. Okay. From 0, that is the higher temperature, minus of -5, so this will be just 5. So the difference you have to take, and the magnitude of that difference has to be positive. That's the main purpose here. Okay. So this is how we do it. Then we need to know that what does the specific heat capacity represent? It represents like how much heat is required to just change the temperature of an object by 1 degree or per unit mass. So it means that higher the specific heat capacity, higher time it will be taken to change the temperature by 1 degree. So higher time means what? If I'm providing some constant energy source, okay, at a constant rate, it means it will just take more time if it has a higher specific heat capacity. Okay. Now, what if the heat supplied is used to change the state of a matter? In this case, it will like Q is equal to ml, and L is representing latent heat. Latent heat expresses the energy per unit mass required to change the state of a matter. So specific latent heat is, there are two kinds of specific latent heat. There is a specific latent heat of vaporization. There is a specific latent heat of fusion. Fusion is related to melting. Vaporization is related to boiling point of a material. So that is something that we should know. Also, boiling point of water, freezing point of water, melting point of water. Okay, so melting and freezing point is basically same only, that is 0 degrees Celsius or 273 Kelvin, and boiling point is 100 degrees Celsius. Okay, that is 373 degree Kelvin. So this is something that should be known fact. Otherwise, other materials information would be given in questions. Another questions that are related to this topics are based on temperature versus time graph. So this is very much important to understand temperature versus time graph, what happens. Okay. So temperature versus time graph. Let's say a object like ice starts from a solid state and we are providing a heat at a constant rate. And what will happen during this change, when it is solid and the temperature is changing, the kinetic energy changes for a material, because the temperature is related to kinetic energy. That's even if this is very repetitive, but we need to remember that in answers, whenever there is a something like theoretical answer they are expecting, always mention that the temperature is related to kinetic energy and then start your answer. Okay, so that is the temperature is changing, kinetic energy is changing. In this state, the potential energy remains constant. Okay, so during the temperature change, potential energy will remain constant and kinetic energy changes. And during the state change, we will expect that the kinetic energy to remain constant. It means temperature does not change or temperature is constant. So in temperature versus time graph, it will show something like a flat line. So this is a like a melting state where temperature is constant. Okay, and at this point, the let's say ice is present, so ice will start melting. Not all the ice will melt immediately, it will take time, and at this point all the ice have all melted. So it, like if you just pick a random point between on this line, it will have both the states, like some of the ice still solid, some of the ice has turned into liquid. Okay, so based on this timeline you can choose how much percentage of, let's say I only want to melt 50% of my ice, so I just have to stop the process where on the half line of this point, so that only 50% of the ice will be melted. Okay, so this is very much important to understand these lines on the graph and what they represent. Okay, and during the state change the potential energy changes. So in case of melting, what is happening is the bonds are breaking. So the bonds are breaking, the particles become bit more free, so the potential energy increases in that case. Okay, uh, so we have to understand, okay, that part. So going from solid to liquid to gas, the potential energy increases due to breaking of bond. Okay, so this causes the increase in internal energy. So throughout the process, the internal energy is still changing, but we need to understand what is causing the change. Is it potential energy or this is the kinetic energy and all that stuff? Okay. Then we need to also understand the gradient of this solid or liquid graph. Okay. When we see at this, when the temperature is changing, the gradient of this graph defines something very much important. It is the gradient of this graph is related to specific heat capacity. Okay. For higher the gradient, uh, the higher specific heat capacity, lower the gradient is what we observe. So let's say liquid has a higher specific heat capacity. It will have lower gradient. Why it will have lower gradient? Because higher specific heat capacity means higher will be the energy required to change the temperature by 1 degree. It means more time it will take for the object to change the temperature. If you have lower specific heat capacity, it means it requires less energy to change the temperature by 1 degree. It means it will require less time. And most of the time, those graphs are provided with constant power supply, okay, or constant rate of heat transfer is what they mention in question. So if they don't mention power, don't get confused. It is just constant uh, rate of heat transfer, and we need to know that power is related to the energy required over time. So most of the time we can calculate the energy that is required by taking power into time, and this energy can be anything. This energy uh, could be mc delta t or whatever. If it is changing the temperature, it can be ml, that can be taken as power into time, and it can be multiple things. So we need to understand, like, we can get information from the graph. If they have given us the power, we can calculate uh, how much energy will be required and how will be the graph will be changing. Okay, so we'll see few examples of this. uh, this is example one. A solar panel transfers the energy at a rate of 2.4 kilowatts to a liquid passing through it. If the liquid has a specific heat capacity of 400 joules per Kelvin, joules per kg per Kelvin, that's the unit. So always remember the units as well. Okay, the temperature of the liquid increases by 6 Kelvin when it flows through a solar panel. What is the flow rate of the liquid through the panel? The flow rate is something that is change in mass about change in time. Okay, so here we can start with the equation that they have given us the power and they have given us specific heat capacity and the temperature change. So the power provided is energy over time, and here the energy is providing is increasing the temperature. So I can replace this with mc delta t over time. Okay. So here, what we required is mass over time. So I can just rearrange this equation by taking all of the known quantities on one side and mass over time on one side. Okay, this is our flow rate. So power is given as 2400 kilowatts. Then this is 4000 and this is 6. Okay, so 6 ones are 6, 4s are 4 ones are 4. So it is like basically 100 over 1000, which will give us 0.1 kg per second. Okay, another problem is related to graph. Okay, so the heat is supplied at a constant rate, or the energy is supplied at a constant rate to a fixed mass. So this is what is required to get a consistent straight line. The mass has to be fixed and the rate has to be fixed. Okay, these are the conditions. They can act sometimes the conditions as well. So conditions are there. It has to be fixed mass and the constant rate. Okay, then only we get a curve like this. What is the statement about is correct about the graph? Okay, so we can see that there are multiple stages here. So I can assume here the stage is starting from solid, then it is going into liquid, and then it is going into gaseous state. So this is the stage of melting. So it is a state of fusion. This is a state of vaporization. Okay. The specific latent heat of vaporization is greater than specific latent heat of fusion, and that is true because the line of vaporization is longer from the graph. So basically, it tells us that it requires more energy for the vaporization process than the fusion process. So this is correct option. But let's see other options are true or not. The specific latent heat of fusion, that is wrong because it is we have just defined that in the previous part. The specific heat capacity of solid is greater than specific heat capacity of liquid. That is again wrong. It is wrong because you can see the gradient of the liquid. The gradient of the liquid is lower. It means it has higher specific heat capacity than the solid. Okay, so we have to compare the gradients to see. Okay, similarly, specific heat capacity of vapor is greater than liquid. Again, not, because we can see that the specific heat capacity of the liquid will be higher because the gradient of the liquid is lowest compared to gas or solid. So this is also wrong for the same reason. Okay. The two ideal gases X and Y are at the same temperature. The mass of the gases is larger than the mass of particle of a gas Y. What is correct about the average kinetic energy and correct about the average speed? Now, if we look at, remember the relationship for average kinetic energy, it depends only on 3/2 kBT. So if the temperature is same for both the gas, the average kinetic energy will be same. So it is either B or C. And average speed, when we talk about, we got a relationship that speed is equal to 3 kBd over m. Now here we can see that the temperature is same, but the mass is different. So mass of x is larger, so velocity of x will be lower. Correct. So velocity of x will be, the speed of the x will be lower. So speed of y is larger. So B is the correct option. Okay. What is the another possibility of the questions? Okay. An insulated tube is filled with large number of n of lead of sphere, each of mass m, and the tube is inverted s times so that the sphere completely falls through a distance l each time. So basically, each sphere is falling distance l each time, and they have mass and there are n number of sphere, and they have repeating the process s time. The temperature change in the before and after the inversion process is delta T. What is the specific heat capacity of the lead? So, so where does the energy is coming from? Change in temperature and energy is related to this formula. They are asking specific heat capacity, so it will be Q is equal to m delta T. Now we know mass of each is m, so I am supposed to take the total mass, so that is n times m times delta T. Where does the heat is coming from? The heat is coming from the gravitational potential energy that the marble like m falls through a distance l each time. So basically, I can take mgh. Okay, that is a one mass, but but since this is just for one lead sphere, there are n sphere, so this is n sphere totally, and they have this process repeated s times, so n get cancelled. get cancelled. I will just get SGH over delta T. Okay. So is there some, instead of H, there is L, I think so. Yes. So this is the correct option. Another problem that we can see in calorimetry, when two objects of different temperatures are brought into contact, what will be the final temperature? So here you can see that two objects X and Y are brought in contact. So for this kind of a question, we should always remember to start with like heat gain is equal to heat lost. So here you can see that the block Y was at higher temperature, it is coming at 60 degrees, so it is losing heat. So this is, and X is gaining the heat. uh, so heat gain is used to change the temperature here. So I can see that gain temperature, mass of X, the specific heat capacity is 2C, and change in temperature is 40 degrees for X. While for Y, it has same mass. No, it has another mass, let's say My, and this is just C, and the temperature change is 20 degrees. So we can cancel out the same part here. So we will get My to be equal to 40, 80M over 20. So that will be just 4M, 4 times mass. Okay. So this is how we can solve any problem. Another example of this is this problem. The mass of ice at a temperature of -5 degrees is changed into water at a temperature of 50 degrees. The specific heat capacity of ice, water, and L is given. What expression is the energy needed for this to go? So usually, in this case, the energy is splitted in multiple parts. It requires energy for multiple things. First, process is like this. So to go from -5 to, it has to go from -5 to 0 in a state of ice. So it is a change in temperature. So MC delta T I will use. So MC delta T, now mass of ice, specific heat of ice, and the temperature change is 5 degrees. Okay. Then the second thing is you need to melt at ice, melt at 0 degrees. Without melting, it won't be possible. So it will require mass of ice and the latent heat. And then you go from 0 degrees to 50 degrees. All three processes has to be required, like performed with energy required, and we have to write an equation. Okay. So this will be mass of ice, specific heat of water. Now because it has changed state, so I will take specific heat of water and temperature changes 50. Okay. So we have to all add up all of this. Okay. We'll get equation like this. Okay. Now sometimes what they might give you some unknown in this equation. Okay, a single unknown, maybe specific heat of ice or mass is unknown or something like this, and they might give like a this is causing the temperature increase is causing by, let's say, water which is at 100 degrees Celsius, and we are adding that ice amount of ice at -5 degrees Celsius. So there is a heat exchange. So you can, this, if this becomes the left hand side, like heat gain by the ice, then the heat loss by the water or some other source can be taken as MC delta T, and how much is the temperature change for other object that is providing the heat can be also taken. So you always work it out with the energy gain or energy loss equation, that is conservation of energy, how we say. And whatever the energy is, you have to be clear exactly what process is happening, and then break down that energy into different processes, and then substitute correct equation to get the correct answer. Okay, so that's it for this. Next, in next video we will talk about method of heat transfer. Thank you so much.